So welcome to my talk that has actually nothing to do with the topics of this workshop. It's not about entanglement, it's not about channels, but the organizers asked me whether I want to give a talk and I said no. So I ended up
Welcome to the club.
No, yeah, because I said I have nothing to say about the topic. So, but if you really need more people, then I can possibly say something. Okay, so I will give my best to entertain you anyway. I want to talk about two recent works that we did in collaboration at the University of Düsseldorf. So the main person here is Lukas Tendik, a PhD student in my group who just finished, and he's now traveling around the world in Vietnam, and I don't know exactly where he is right now. Martin Klich, who was a junior professor in Düsseldorf and recently moved to Hamburg, where he got a permanent position. Hermann Kampermann, long-term permanent member in my group. So we wanted to look at sets of measurements and the interesting topic of incompatibility, which is also nowadays much studied. And we looked at it in the context of resource theories. So a lot has been done about resource theories of states, but not as much in resource theories of measurements. So, well, I'm a little bit exaggerating if I say a new measure. It's not at all a new measure, but in this context, it has not been used as far as we know. And well, it's a distance measure, and distance measures are nice because you can do lots of nice things with them. And I will show that there are some inequalities for sets of measurements, which somehow reveal a kind of polygamous nature of incompatibility. That's a brief summary. My talk, well, I will basically set the notation and remind you of what are sets of measurements. I will introduce this distance measure that we suggest to use in this context of resources of sets of measurements. And if I talk about resources, it's not only about incompatibility, but there are other types of resources. Or maybe the most trivial one is informativeness, then there is coherence, steerability, non-locality, which Reinhard doesn't like, but I will call it like that.
I don't like the term.
You don't like the term, exactly. Exactly, yes. But more about that in a moment. And I will show you some inequalities for measurement incompatibility in both directions, upper bounds and lower bounds. If you want, you can read up the details in these publications. One was published in Quantum recently, and the other one is on the archive. So let's fix the notation. What do I call a measurement? One measurement is a POVM, so a set of elements that are positive semi-definite, and they have an index A, which numbers the elements, and all these elements MA sum up to the identity in a d-dimensional space. So actually, I don't even talk about infinite dimensions. Everything is finite dimensional. So again, I don't fulfill the requirements for talking about the topic of this workshop. Never mind. So index A denotes the outcome of the measurements, and the probability to find outcome A is given by Born rule trace MA times rho. So here's an example that maybe you cannot read, I'm sorry. So it's the Bloch sphere, here up is the state 0. So if you project onto state 0, this could be measurement element M0, and if you project on state 1, it's M1. Okay. Now, today I want to talk about measurement assemblages or sets of POVMs, so sets of sets. And then I need the second index. The index X denotes now the measurement setting. And again, the index A denotes the outcome for a given measurement setting X. So each of these elements still has to be positive semi-definite. And for all measurement settings X, the elements MA given X add up to the identity. And here you have a very prominent example, like in the BB84 QKD scheme, where you have one measurement in the Z basis. So the second index denotes measurement 1, and you have operators M0 given 1, M1 given 1. The second measurement is, for instance, in X direction, where you have the second setting and element M0 given 2 and M1 given 2. So that's my notation. And I'm going to talk about such measurement assemblages. But before I come to these inequalities, let me go to measurements in the context of resource theory. So definitely we are not the only ones or first ones who talked about resource theories of measurements, but most people actually talk about resource theories for one measurement. So not so often you see something about sets of measurements or assemblages. So there's a lot of literature that I've cited here. And as in every resource theory, also in the resource theory for measurements, you have certain ingredients that here are listed in words, and then I will go a little bit more concretely into that. So you have free measurements, which are here denoted as this convex set. These are free measurement assemblages that do not carry a given resource. So once you fix the set of free measurements, you will somehow fix together with the free operations also the whole resource theory if you also have a quantification of the resource. So outside of this free set of measurements, you have resourceful measurement assemblages, and the so-called free operation is an operation that cannot take you outside from inside this free set, outside of this free set. So any free operation lambda, and I will say in a minute what I mean by that, will take a measurement assemblage, let's say F, to another measurement assemblage G, but cannot go outside of this free set. Then in order to go outside, you need resource increasing operations. Well, such a free operation is also denoted here in the resourceful measurement assemblages. It can take, for instance, a measurement assemblage M to one called N, but it can only decrease the resource. It can never increase the resource. And here I've already indicated kind of intuitively a distance. So this measurement assemblage M has a distance to the set of free measurements, dm, and the distance can only be decreased by a free operation. Second ingredient are the free operations. The third one, the quantification of the resource. And all these together form a resource theory. So let's go into a bit more concrete detail for sets of measurements. So the free measurements, I denote with a letter F, A given X. So for instance, if you fix the free measurements such that they are diagonal projectors with certain coefficients, positive coefficients, then you get the resource theory of coherence. And any measurement that is not of this form is an incoherent, any measurement that is of this form is incoherent, and if you have off-diagonal elements, then you have a resource of coherence. So what about operations? Free operations do not increase the resource. So there are different ways to define these operations. So if you remember the action of CPTP map on a state row, that can always be written in the Gauss form with Gauss operators KMU and KMU dagger, then you can define the adjoint map lambda dagger that acts instead on the measurement operators because the trace of these POVM elements, MA given X times lambda of rho, can be written with the cross operators. Under the trace, you can shuffle the A dagger to the front, and that means that you act with the adjoint map on the POVM element. So this is one option to define a free operation via the adjoint map lambda dagger. Another option is, for instance, to define a map that consists of mixing POVM elements and doing classical post-processing. So you can define a new measurement assemblage prime as psi of M, where you mix the old elements with certain coefficients, and then you do that with certain post-processing probabilities. So these are possibilities to define operations. And then for the quantification of the resource, we want to suggest a monoton. And we typically want in these resource theories monotons with certain properties, namely the measure R of the set of measurements is 0 if and only if the measurement assemblage is in the set of free measurements. Sorry, this should be a different symbol than here. It's a typo. And for free operations, either these adjoint maps or post-processing maps, they can only decrease the measure of the measurement assemblage, the resource in the measurement assemblage, and convexity is the last property that we wish for such a monotone. And well, there are different types of measurement resources. So as I said before, a lot has been said about individual measurements, so just one PUVM. And so the most primitive or trivial resource is informativeness, which means that free measurements are those which are proportional to the identity with a certain probability. So you learn nothing. So as soon as you deviate from the identity, you have the resource, you get some information. Then I already mentioned coherence. If the free measurements are incoherent, then you get together with the measure and the operations, the resource theory of coherence of measurements. And yeah, these are two typical resource theories for individual measurements. What about a set of measurements? There, a very prominent resource theory is the one of incompatibility, where of course you need at least two measurements. And so how do we define the free measurement assemblage? There are again different possibilities, Ottfried Güne and others. They are not the only ones, but it's very common to define the free measurement assemblage as those measurements which can be simulated by a single parent measurement, V, the convex lambda, and deterministic classical post-processing. So when I write a small v, it's a deterministic probability distribution only bringing entries 0 and 1. And necessarily, if you want to have an incompatible set of measurements, you need operators that do not commute, but the reverse is not necessarily true, as we will also see in a moment. So then there is the option to combine the resource of a set of measurements with the resource of a state of states. And there you arrive at steering. So an unsteerable state assemblage is given such a way where you have a state row and a measurement acting only on, so a composite state row, at least two subsystems. And the measurement, let's talk about bipartite systems for simplicity. The measurement is only acting on one half of it. And it's unsteerable if you get, if you can get it from, again, the deterministic probability distribution of states sigma lambda. And finally, many people call this property non-locality. Not everybody likes this word, but let's stick to it because it's yeah, common in the community. So a local, so-called local probability distribution, which is free in that sense that it cannot violate a Bell inequality, is given in such a way that you have a bipartite state row. You act on both sides with the measurement. If you can write the resulting probability distribution as such a product of deterministic probability distributions for Alice and for Bob with a hidden variable lambda with a certain probability distribution, then it's called non-local. Then it's called local, sorry. Okay, so we wanted to define a more unified framework for resource theories of measurements by defining a quantifier, a measure where you can somehow link all these resource theories. Mostly the quantification of this resource in quantum measurements is done by robustness measures, which work typically as follows. Well, here you have the free set. It's a little bit different picture from the one that I had before. Then you have a measurement assemblage outside, and you take the minimum of a positive number S such that there exists another measurement assemblage N, and you add this other measurement assemblage with prefactor S such that you move it inside this set of free measurement assemblages. So in that sense, the more you have to add, the more robust the assemblage is against disturbances. So this is a measure that has been used a lot, but it's not so nice in a mathematical sense. It's not well behaved in the sense that it may be infinite, it can have strange properties. etc. The triangle inequality, I think it does not hold. No, I'm not sure, but maybe, I think not in general. Okay, so we wanted to introduce a distance-based measure because it has very nice properties. So we suggested the following resource monotone. We take a certain distance that I'm going to define in a moment between our measurement assemblage M and any free measurement assemblage. And it has all the properties of a distance. It's positive if and only, well, if M is not equal, it's not a free measurement assemblage, is positive, it's symmetric, fulfills triangle inequality. And our suggestion is to use a channel. So there is a certain link to channels, but a very weak link to channels. So we suggest to define a measure and prepare channel associated with every QVM. So our channel lambda associated with a measurement mx acting on the state rho is given as follows. We take the trace of the PUVM element MA given X times rho, and then we take the projector onto the outcome A. So we define the channel that corresponds to our measurement. And the distance that we use is the diamond distance between channels that has been studied a long time ago and used, for instance, in channel discrimination. And it can also tell you something about how entanglement can help to increase channel capacities, etc. So you apply, so the distance, diamond distance between two channels, lambda 1 and lambda 2, is the difference of these channels, tensor something in any dimension, acting on any density operator in any dimension, and then you take the trace norm. So you basically, it's the trace distance of these two channels extended in any finite dimension.
Sorry if
Yes.
I ask. So you have a fixed basis around for everything.
Yes.
Because then
Yes.
otherwise this would
Yes.
be
Yeah,
the basis. And if you get the wrong one for lambda 2, then you have a fake distance that you don't want.
Okay. Well, but our outcomes are, they have indices as, so yeah, no, you're right. Yes, if I would choose different ones, I would get a fake distance, but I don't do that. So. But you're absolutely right. Good, and now we can define a distance measure for all of these resource theories, and it's a little bit boring to go through all of this, so let me just explain it once. For the informativeness, the diamond norm of such a measurement assemblage, here is an extra index P. In principle, you can also put weights on the different measurements. So if you see this vector P, it means a weighted measurement assemblage, that is also covered by this formalism. So you take the diamond distance for our measurement, our channel associated to measurement MX, and the free one, you minimize over all free measurement assemblages and you put the weights in front. So you average over all measurements. And we also think that it's not a very clever measure, but we haven't found a better one. We are now thinking to make it.
Can I ask you? So
yes,
for QC channels, the diamond norm should simplify quite a lot. And then this should become dual to the one norm. And this
yes,
should be like guessing probabilities at the end.
yes.
So
that's true. Yeah, I mean, it's this diamond distance is something that is well known. No, we're not saying that we invented this. We're just using it in this context of measurements.
that you don't need this extension, right? Basically, for a QC channel.
Yeah, you can.
But we don't have this QC channel.
Measurement.
Yes, measurement is a
You
QC.
take, no, that's,
Um,
it produces the classical states. No?
okay, in this sense, because it's a
Yeah, but if,
Yeah, but the ancilla is still useful. I mean,
but if
the-
you have
we talked
different
about-
outputs, they are not in the same they're not in the same classical space. So the re-implementation
Mhm.
matters.
yeah. If you have
If the A is the same A, you're right.
the A is the same
Is it?
A, it's classical, yes.
Yeah, then it's
But also-
QC.
But you also have different measurements, and there you cannot, I mean, if you have a measurement in Z and in X direction, you cannot simply say it's classical, because then it really matters.
No, the input is quantum. the output
Yes.
is class like an abelian algebra.
But it's not simple to calculate.
Okay, sorry.
Yeah, no, but it's. Good. And then basically we do the same for all of these resources that I just mentioned. I talked about coherence, so we do the same there. Only the set of free measurement assemblages is different now. For incompatibility, the same thing, and it changes a little bit for steerability, because then you have to, well, you can define the trace norm between the resulting density operators on the one side. And for non-locality, you get the distance between two classical probability distributions. But because the diamond distance is defined by the trace norm, you can link all these quantities in a kind of hierarchy. That's our result. So by construction, there is a nested structure for some types of these measurement resources, because any uninformative measurement is by construction also incoherent, because it's proportional to the identity, and it's also jointly measurable. So we have a nested structure of these three sets, and that leads to the immediate conclusion that informativeness is always larger or equal to coherence, and coherence is always larger or equal to incompatibility. And in fact, one can, so this is the first, these are the first two inequalities of a kind of hierarchy between these five resources, and one can extend this hierarchy also to steerability and to non-locality, as introduced before. So the first two inequalities are trivial, as I showed before. And for this third inequality, you can use for the proof a state assemblage that results from the closest joint measurable measurement. And this gives you an upper bound on steerability, because to steer, you always need incompatibility. And the fourth inequality, similarly, you use a probability distribution resulting from a measurement on the closest local hidden state assemblage. And you can never produce non-locality, you can never violate Bell inequality, and that gives you the last inequality sign. So in this sense, these different resources can be ordered when you use this distance measure. So this is one of the results or the revelations that this distance measure allows you. Good, and then you can play around. You can write STPs, you can find numerical solutions. So already John Watrous, long time ago, showed how to construct STPs for the diamond distance. So we used his work. And you can also find some analytical solutions in this way, because if you have a feasible solution of the primal problem, this is an upper bound. Feasible solution of the dual problem, it's a lower bound. And if they coincide, then we also have tight bound. And then, well, let me mention some interesting examples for incompatibility, some analytical results. And well, typically one thinks about MUBs. So if you have a measurement in the mutual unbiased basis, for each of these QVM elements is a vector that corresponds to a mutually unbiased basis. So whenever X and Y are different, then the vectors have an overlap of 1 over square root t. And then we get upper and lower bounds for the incompatibility of such a set of MUB measurements. And this depends on the dimension. So we have a lower bound and an upper bound, depending on the dimension d and on m, the number of bases. So for instance, if you have a large d and a fixed m, then the incompatibility is actually equal to 1 minus 1 over m, and the limit of d going to infinity. For a while, we hoped that we could find some results for mutually unbiased bases by some contradiction that an upper bound is lower than the lower bound or something, but we didn't manage, of course. So, but let me say that even in those cases where we nowadays don't know yet whether MUBs exist. So for instance, in dimension 6, we don't know whether 4 mutually unbiased bases exist. If tomorrow somebody comes and tells me, yes, they exist, then we can immediately provide bounds for this situation. So here, these bounds are general for any D and M. Good. So let me go to the next step. So after introducing this distance measure, we asked ourselves what happens when you modify your set of measurements. So let's say you start with 2 measurements, like in the BB84 protocol. For QKD, you measure in the Z and in the X direction, but then there is another protocol called the 6-state protocol where you also measure in the Y direction. So what is your incompatibility gain when you add another measurement? That was the fundamental question that we wanted to answer. So how much incompatibility gain, delta I, can you gain when you add a measurement to an assemblage? So right now, the next transparencies are always about going from 2 to 3, but we can also generalize this. So, but for didactic purposes, I think it's easier to digest if we look at this example. So this delta I is the diamond distance, the incompatibility of a measurement assemblage consisting of 3 measurements minus the one consisting of 2 measurements. So the symbol M with 3 indices means an ordered list of POVMs, and I get it by concatenating the list of 2 measurements M1, 2 with the 3rd measurement M3. So this symbol, we didn't know what symbol to use, but I think this is kind of intuitive, explainable. So we have 2 lists and we concatenate them. And I don't want to go through the technical details, but I want to show you 2 of our results, one upper bound and one lower bound. There is one upper bound. This gain of incompatibility is upper bounded by the incompatibility of a certain measurement assemblage that consists of the concatenation of the closest jointly measurable assemblages to the subsets that each consist of 2 measurements. So here the notation is as follows. M with this sharp means with the indices ij is the closest jointly measurable assemblage to mij. So closest in the sense of the diamond distance. So here n is the concatenation of the closest jointly measurable assemblage of measurement 1 and 2, concatenated with the closest one for 1 and 3, concatenated with the one for 2 and 3. And the gain is upper bounded by the incompatibility of this measurement assemblage. Good. How does one prove this? I don't want to show the proof, but it's basically very simple. There are 2 elements. The first is the idea that we split the whole measurement of 3 POVMs in such a way that we have 6 measurements, out of which some are identical, and we group them in pairs. So it's just of course, we have flat probabilities for the moment. If I don't write any weight, I assume flat probability. So before we had probability 1/3, measurement 1, 2, and 3. Now we have 1/6, measurement 1, 2, 1, etc. Okay, and then of course the incompatibility is the same if I make the splitting. The second proof element is the triangle inequality, which works for the diamond distance. And here you see a picture that looks at first sight almost like the picture for entanglement of 3 qubits in very old papers. But it's of course very different. It's only a similarity in the abstract picture. So the picture is explained as follows. You have 3 convex sets. JM1, 2 means jointly measurable set of measurement 1 and 2. Then here another set for 2 and 3, another set for 1 and 3 jointly measurable. But if measurement 1 and 2 are jointly measurable and measurement 2 and 3 are jointly measurable, it does not necessarily mean that all 3 are jointly measurable. So this is this inner red circle where all 3 measurements are jointly measurable. Then you have the convex hull of these 3 sets. And everything that is outside of this convex hull is a measurement assemblage that is, how is it called? It's genuine triple-wise incompatible. It's not by us, this picture. Sorry, I should have put the original reference. So, and if you have a measurement that sits, for instance, outside here, and you want to determine its incompatibility, which is given by the distance to the jointly measurable set, this red one here, you can pick any point in between. So here, for instance, it's M sharp of the first and second measurement, concatenated with the third one, and you can use this for the triangle inequality, and then you get an upper bound. So that's the method. Here's an example for the QKD example that I mentioned before. So here you see the incompatibility as a function of noise parameter eta. So here we took white noise. So eta equal to 1 means no noise, and eta equal to 0.5 means that you have 0.5 times the projector plus 0.5 times normalized identity. The blue line is the incompatibility for 2 Pauli measurements. So we have a set of 3 Pauli measurements, X, Y, Z. You can pick any 2, and you get this blue line. And if you take all 3 Pauli measurements, you get this kind of purple-violet line. And the red line is the incompatibility of this measurement assemblage that are called N. And here, in fact, the bound is tight, because if you see that the blue line plus the red line give the purple line. And here you also see that, well, X, Y, and Z never commute, but there is a certain parameter regime where the incompatibility is 0 anyway, because you can find this parent POVM. That's from which you can derive the measurements. So in this example, our bound is tight. Good. Let's go to the last, I think, last slide. So again, how much incompatibility can we win? We found a lower bound as well. So we can show that the incompatibility of the set of 3 measurements is lower bounded by 1/3 of the incompatibility of the subset of 2 measurement 1 and 2 plus 1 and 3 plus 2 and 3. And again, for the proof, we need the properties of the diamond distance and convexity. And for the interpretation, well, we see that in order to have a high incompatibility of the whole assemblage, we need the fact that each of the 3 subsets has to be highly incompatible. So, which is intuitively also understandable, but we call this kind of the polygamous nature. Assemblage of 3 measurements can only be highly incompatible if all subsets are highly incompatible. And this is quite different to entanglement. So even if the 2 pictures look a little bit similar, the properties that arise are very different. So in entanglement, as all, if you remember, we have these monogamy inequalities that 2 parties, Alice and Bob, can, if they are maximally entangled, then Bob cannot be entangled with Charlie. And there are some inequalities in a similar spirit, but very different interpretation.
Sorry, can you
Yes.
explain this a bit more? I thought there are examples where of 3 measurements where any pair is compatible, yet the triple is not. So it could be that
Yes.
the right side is
Yes,
0.
this bound is not always tight. Sorry.
Yeah.
This bound is not always tight. So we are just saying, yes, you said that if they are all compatible,
The right side is
nevertheless,
0.
the incompatibility can be non-zero.
Yeah, yeah.
This is contained here. So this bound is not always tight. There are examples when it's tight,
Yeah.
but you are mentioning it. So maybe
maybe
I
I
should.
don't understand your interpretation then. Never mind.
Okay, so you say that.
It's like it seems to say exactly the opposite. There are this example where all the pairwise subsets are
Okay, only in those cases when it's
highly
tight. Yes,
compatible.
yes, yes.
In fact, perfectly compatible.
Oh, you're right. This interpretation at this point is yes. Thanks a lot. No, here it's the interpretation at this point is not correct. It's correct when the inequality is tight. For this example, it's not tight. Yes.
Okay.
So maybe I should formulate it the other way around. So it's possible that all of the subsets are maximally incompatible. and lead to maximal incompatibility of the whole set, which in entanglement is not possible, that all of the subsets are highly entangled.
Yes, yeah.
Yeah, sorry, I said it in the wrong way though. So
Okay.
thanks
Yes.
for paying attention. Yes, I know you're absolutely right. Good, so we can generalize these inequalities to more than 3 measurements and also to weighted measurement assemblages. But if you are interested in the details, you can just have a look or talk to me, and I'm summarizing in time, luckily. So I talked about resource theories for quantum measurements. We suggested a quantifier, namely the diamond distance. We showed that there is a certain hierarchy between these different resources of measurement assemblages. And we found certain inequalities for the gain of incompatibility when you add a measurement. And there are many future directions where we want to go. So relations to other resource theories. So I think in the morning there was a talk about real, well, what happens to entanglement in real spaces. And yeah, unfortunately I could not be here. So what happens when you look at resource theories of imaginarity? Is there a new interpretation? What changes there? Also, there are entropic resource quantifiers for sets of measurements. Is there any interesting to be said? Is there a link? So for instance, for the robustness measures, parts of this hierarchy that I showed also hold true for robustness measures, but not all of them have been shown to be true or have been disproven. So there are some open ends. And well, tightness of parts of the hierarchy, for 2 of these 4 inequalities, we could show that they are tight, but the others are probably not tight, but we were not able to prove it. And finally, all of this is for finer dimensions. And of course, if anybody of you can tell me how to do it for continuous variables, then maybe this might even be something for the open discussion. If somebody, an expert, knows how to do it, I don't know how to do it, but this will be interesting. Well, and last but not least, maybe the most important transparency, my group in Düsseldorf. And where's Lukas? The main guy, Lukas Tendig, is here in the sunny Southeast Asia. Hermann Kampermann, who runs the group when I'm away like here. Without him, it would be impossible to run such a big group. So that's all I wanted to say. Thanks for your attention.